In this lecture, I am going to present the analysis of sway frame when the load is present on the horizontal and vertical members. So this is the problem. Analyze the frame shown in figure and draw bending moment diagram. So this is the frame, this is the vertical members, and this is horizontal member. So there is present two concentrated load, one on the horizontal member and one on the vertical member. The 80 kilonewton load is present at the midpoint of the horizontal member, and 40 kilonewton load is present on the vertical member AB, that is at a distance 3 meter from the support A. The length of AB is given 4 meter and BC is given 6 meter and CD is given 4 meter, and the moment of inertia of AB is given I and BC is given 2I, CD is given I. Let delta be the sway in the figure 2. So this is the figure 2 and this is the sway takes place delta amount due to the horizontal loading. The axial deformation in member BC is assumed to be negligible, hence both columns sway by same amount. So here both the columns sway by same amount due to the negligence of the axial deformation. As you know, the first step, so you have to find out the fixed end moments. So here you see, so this is the vertical member AB and this is horizontal member BC and CD is the vertical member. So on the vertical member AB there is present 40 kilonewton load at a distance 3 meter from the support A and 1 meter from the joint B. Here you have to treat 40 kilonewton load as a eccentrical loading. So you have to find out what is the fixed end moment MFAB and MFBA. Similarly, on the member BC there is present the concentrated load 80 kilonewton at the midpoint of BC. Here you have to find out the fixed end moment MFBC is equal to minus WL by 8 and MFCB is equal to plus WL by 8. And on the member CD, so there is no load. Here the fixed end moment 0 at both ends. So the fixed end moment MFAB, that is equal to minus WAB square by L square. So here you have to take A is equal to 3 meter and B is equal to 1 meter. So MFAB is equal to minus 40 into 3 into 1 square by 4 square. Minus 40 into 3 into 1 square by 4 square. So this is equal to minus 7.5 kilonewton meter. Then MFBA is equal to plus W A square B by L square. 40 into 3 square into 1 by 4 square. 40 into 3 square 1 by 4 square. So this is equal to 22.5 kilonewton meter. Then on the span BC there is present the point load at the midpoint of the BC. So here the fixed end moment MFBC is equal to minus WL by 8 and MFCB is equal to plus WL by 8. So MFBC is equal to minus 80 into 6 by 8. This is equal to minus 60 kilonewton meter, and MFCB is equal to plus 80 into 6 by 8. So this is equal to 60 kilonewton meter. Then on the vertical member CD there is no load. So here the fixed end moment MFDC and MFCD both are 0. Then what are the end conditions? As you know, at the fixed end, so there is no rotational displacement. So the theta A is equal to 0. Similarly, at support D, due to fixed end, here also there is no rotational displacement, so theta D is equal to 0. And at the joint B, so the rotational displacement takes place, that is theta B, and at joint C the rotational displacement takes place, that is theta C, and the translation displacement delta E takes place in the vertical members. So here there are three unknown displacement. So one rotational displacement at B, and the second rotational displacement at C, and one translational displacement delta. So three unknowns. Here you need three equilibrium equations. So the first equation you have to take at joint B, and second equation you have to take at joint C, and third equation you have to find out from the horizontal shear in the column. So then you find out the slope deflection equation. So as you know, the formula MAB is equal to 2EK 2 theta A plus theta B minus 3 delta by L plus MFAB. Similarly, MBA is equal to 2EK 2 theta B plus theta A minus 3 delta by L plus MFBA. You know K is the relative stiffness of the member, so that is equal to the moment of inertia by length of the span. So for span AB, so the slope deflection equation MAB is equal to MFAB plus 2EI by L, 2E and I and L is given 4 meter, 2EI by 4 into 2 theta A plus theta B minus 3 delta by L, but theta A is equal to 0. MAB is equal to, and you know what is the fixed end moment MF AB, MFAB. So already you got here MFAB is equal to minus 7.5 kilonewton meter. So here you put MFAB is equal to minus 7.5 plus 2 EI by 4 into 2 theta A plus theta B minus 3 delta by 4. But we know theta A is equal to 0. So after putting the theta A value here, so MAB is equal to minus 7.5 plus 0.5 EI theta B minus 0.375 EI delta. Then take MBA. So MBA is equal to MFBA plus 2 EI by L into 2 theta B plus theta A minus 3 delta by L. So you know MFBA is equal to 22.5. So here you put MBA is equal to 22.5 plus 2 EI by 4 into theta A plus 2 theta B minus 3 delta by L. So L is equal to 4. So you know theta A is equal to 0. So here you put theta A is equal to 0. Then after simplification, MBA is equal to 22.5 plus EI theta B minus 0.375 EI delta. Then find out MBC. MBC is equal to MFBC plus 2 EI by L into 2 theta B plus theta C minus 0. So there is no extension of the member. So in a horizontal member, so the delta is equal to 0. So you know MFBC is equal to minus 60 kilonewton meter. So here you put MBC is equal to MFBC minus 60 plus 2E into 2I. So here given for BC span, the moment of inertia is equal to 2I and the length is equal to 6 meter. So here you put 2E into 2I by 6 into 2 theta B plus theta C minus delta is equal to 0. Then after simplification, MBC is equal to minus 60 plus 1.333 EI theta B plus 0.667 EI theta C. Then find out MCB. So MCB is equal to MFCB plus 2 EI by L into 2 theta C plus theta B minus 0. Delta is equal to 0. And you know MFCB is equal to 60 kilonewton meter. So put the value in this equation. So MCB is equal to MFCB 60 plus 2E into 2I by 6 theta B plus 2 theta C minus 0. So after simplification, MCB is equal to 60 plus 0.667 EI theta B plus 1.133 EI theta C. Then find out MCD and MDC. MCD is equal to MFCD plus 2 EI by L into 2 theta C plus theta D minus 3 delta by L. So here you have to consider the delta. Here you have to consider the delta minus 3 delta by L. So you know MFCD is equal to 0 and the moment of inertia of CD is equal to I and the length of CD is equal to 4. So put the value here. MCD is equal to 2 EI by 4 because MFCD is equal to 0. 2 EI by 4 into 2 theta C plus theta D minus 3 delta by 4. But we know theta D is equal to 0. So here you put the value of theta D and MCD. Then after simplification, so you get MCD is equal to EI theta C minus 0.375 EI delta. Then find out MDC. MDC is equal to MFDC plus 2 EI by L into 2 theta D plus theta C minus 3 delta by L. So here MFDC is equal to 0. So put the value here. MDC is equal to 2 EI by 4 into theta C plus 2 theta D minus delta by 4. So here you know theta D is equal to 0. So put the value of theta D here. Then MDC is equal to 0.5 EI theta C minus 0.375 EI delta. So these are the slope deflection equations. Then coming to the equilibrium equations. So here you get the first equilibrium equation at joint B, that is the summation of moment at B is equal to 0. So at joint B there are two members meet, BA and BC. So the MBA plus MBC, that is equal to 0. MBA plus MBC is equal to 0. So here you put the value of MBA and MBC. So you know MBA is, this is the expression, and MBC this is the expression. So put this expression in this equation. Then after simplification, so this is the equation 1. Then the next equilibrium equation you get at the joint C, that is the summation of moment at joint C is equal to 0. Here you take MCB plus MCD, that is equal to 0. Then you know what is the value of MCB and MCD. So this MCB and MCD that you put in the equilibrium equations. So after simplification, so here you get this is the equation 2. Then the third equation will be obtained from the horizontal shear in the vertical members. So consider the free body diagram of column as shown in figure 3 and taking moment about top joints. So here you take the vertical members, that is the column AB and column CD, and you take the moment about the joint B for column AB and from joint C for column CD. This is the moment, the clockwise positive moment. This is MAB and here this is MBA, and this is the load is acting at a distance 1 meter from the joint B, and this is the horizontal shear at A, and the vertical shear that is passing through the axis of the beam. So this is cancelled. So here you have to take the horizontal shear at A, and this is the load, and this is 2 moment. You have to take the moment about the joint B. Here MAB, this is clockwise moment, MBA, this is clockwise moment. So this is clockwise moment, that is equal to the anti-clockwise moment. So the anti-clockwise moment you get due to this load and due to the horizontal shear. So due to this load, the anti-clockwise moment is 40 into 1, and due to the horizontal shear, anti-clockwise moment is equal to HA into 4. So HA into 4 plus 40 into 1 is equal to MAB plus MBA. Then 4HA is equal to MAB plus MBA minus 40. So after getting this expression, so you know what is the value of MAB and the MBA. So put here the MAB and MBA value, then finally you get 4HA is equal to 1.5 EI theta B minus 0.75 EI delta minus 25. Similarly, so take the column CD and take the moment about the joint C. So here this is the moment MDC and this is the moment MCD, both are clockwise moment, and the horizontal shear at D is HD. So take the moment about the joint C. So here the clockwise moment is equal to anti-clockwise moment, that is MDC plus MCD, that is equal to SD into 4. HD into 4 is equal to MCD plus MDC, and you know MCD and MDC value. So here you put the MDC and MCD expression, and after simplification you get HD into 4 is equal to 1.5 EI theta C minus 0.75 EI delta. Then you take the sum of the horizontal shear is equal to 0. So here this is the horizontal shear at A, this is horizontal shear at D, and this is the horizontal load which is acting on the vertical member. So HA plus HD plus 40 is equal to 0. Then you multiply here by 4HA plus 4HD plus 160 is equal to 0. So here you know 4HA is equal to 1 EI theta B minus 0.75 EI delta minus 25, and here 4HD is equal to 1.5 EI theta C minus 0.75 EI delta. So put the value of 4HA and 4HD in this equation. After simplification, here you get the third equation, EI theta B plus EI theta C minus EI delta is equal to minus 90. So this is the third equation. Then simplify the equation 1, 2 and 3. So this is equation 1 and this is equation 2 and this is equation 3. Here there are 3 unknown, theta B, theta C and delta. Simplify these 3 equations, and after simplification, so you get what is the value of EI theta B, EI theta C and EI delta. Here you get EI delta is equal to 110, EI theta C is equal to minus 19.25 and EI theta B is equal to 39.25. Then after getting this, find out the final moments. So substituting the value of EI theta B, EI theta C and the EI delta in slope deflection equations, we get MAB is equal to minus 7.5 plus 0.5, 39.25 minus 0.375, 110 is equal to minus 29.12 kilonewton meter. Then MBA is equal to 22.5 plus 39.25 minus 0.375 into 110 is equal to 20.5 kilonewton meter. Then MBC is equal to minus 60 plus 1.333 into 39.25 minus 0.667 into minus 19.25 is equal to minus 20.5 kilonewton meter. Then MCB is equal to 60 plus 0.667 into 39.25 plus 1.333 into minus 19.25 is equal to 60.51 kilonewton meter. Then MCD is equal to minus 19.25 minus 0.375 into 110 is equal to minus 60.51 kilonewton meter. And MDC is equal to 0.5 minus 19.25 minus 0.375 into 110 is equal to minus 50.875 kilonewton meter. So here you see, so at joint C the sum of the moment should be 0. So here you check it, MCB plus MCD should be 0. MCB here you see 60.51 and MCD minus 60.51. So sum of these two moment is equal to 0. Similarly at joint B the sum of the moment is equal to 0. MBA plus MBC is equal to 0. So MBA here you got 20.5 and MBC you got minus 20.5. The sum of these two moment is here equal to 0. The final moment what you are getting from the slope deflection equation, that is correct. Then draw the bending moment diagram. So for the bending moment diagram, these are the support moment, and you have to find out the free moment, that is the positive moment due to the external loading. So first find out the free moment in column AB. So this is column AB. So due to this load, so find out the free moment or positive moment. So here the load is present eccentrically. So what is the positive moment? You know that is in simply supported beam when the load is present eccentrically. So what is the maximum positive moment at the loading point? That is WAB by L, 40 into 3 into 1 by 4. 40 into 3 into 1 by 4. So this is equal to 30 kilonewton meter. Similarly, find out the free moment in span BC. There is present the concentrated load at the midpoint. So what is the maximum positive moment at the midpoint? That is equal to WL by 4. So W is equal to 80 and L is equal to 6 by 4. 80 into 6 by 4. So the maximum positive moment on span BC at the midpoint, that is equal to 80 into 6 by 4 is equal to 120 kilonewton meter. Then after knowing the positive moment for column AB and for span BC, then you can draw the bending moment diagram. So here you will see MAB is equal to minus 29.12, MAB is equal to minus 29.12 kilonewton meter, MBA 20.5 kilonewton meter, MBC minus 20.5 kilonewton meter, MCB 60.51 kilonewton meter, MCD minus 60.51 kilonewton meter, and MDC minus 50.875 kilonewton meter. So give the direction of the moment. So MAB minus 29, as the moment is negative, so the direction is anti-clockwise. This is MAB anti-clockwise, and MBA this is 20.5 plus. So here you give the clockwise direction, clockwise, and MBC minus 20.5. So here you give this is anti-clockwise, and MCB this is 60.51 positive. So here you give MCB this is clockwise, and MCD minus 60.51. So here this is negative. So here you give anti-clockwise, and MDC minus 50.875. So this is also anti-clockwise direction. So these are the direction of the moment. Then after giving the direction of the moment, then you can draw the negative bending moment diagram first. So here this side is your MAB outside. So here you take MAB 29.12 and the MBA take this side 20.5. Then join this 2 point, and this is the negative moment. And here also at B MBC minus 20.5 this side. So here you draw 20.5, and MCD this is MCB 60.51 this side. Take here 60.51, then join these 2 points. This is the negative bending moment diagram. Similarly, MCD this side you take 60.51, and MDC inner side you take 50.875, and join these 2 points, and this side is negative and this side is positive. So the tension inside that you have to take positive. So this is the value. So here 29.12, this is 20.5. So this is the negative moment diagram, and here this is 20.5, this is 60.51, and this is the negative bending moment diagram, and here this is 60.51 and this is 50.875, and this is the, you draw this 2 point, and this portion is negative, this is positive. So the tension inner side you take positive. Then due to the loading, so you have to draw the positive bending moment diagram or free moment diagram. So on the vertical member, at the load is concentrated load, here the free BMD is triangular. So here you got 30 kilonewton meter. Here you got, this is 30 kilonewton meter. That is the maximum positive moment at loading point in column AB. This is the loading point in column AB. This is 30 kilonewton meter. Here from this to this 30 kilonewton meter. And here also due to this concentrated load, so here you got the free moment or positive moment 120 kilonewton meter. So this is also triangular. This is also triangular. Here this portion, the positive negative cancel each other, and here also this portion, the positive negative cancel each other. So here this is the remaining negative, this is positive, this is negative, this is negative, this is positive, negative, negative, positive. These are the final bending moment diagram. Then you have to find out what is the maximum positive moment here and what is the maximum positive moment here. You know how to find out this maximum positive moment. So here you have to draw one line parallel to this line, and you have to take two similar triangle here. Here you have to take one large triangle, and here you take another small triangle and find out this ordinate. Then you find out this total ordinate, and from this total you deduct this ordinate, 30 minus this ordinate. So you get what is the maximum positive moment in the column AB. Similarly, you can find out what is the maximum positive moment here. So here also you draw one line here parallel to this horizontal line and make two triangle. So one triangle this one and another triangle this one, and find out this ordinate. Then you know this one 20.5. So find out the total ordinate here, and here you see this is 120 kilonewton meter, and you deduct this portion, so that you get what is the maximum positive moment here. So this is the complete bending moment diagram of the sway frame. Now all are clear how to solve the problem when there is present the concentrated load in the horizontal member and in the vertical member